Hello and welcome to the first video of the online course Easy Geosteering. In this course we break down the main geosteering topics into easy-to-follow steps, presenting them in a clear and logical way. Here is the structure, and the course contains four main parts: necessary theory, BHE components and LWD login, then modern geosteering tools, and finally a deeper dive into the relevant MLWD technologies. And first of all, let's set a high goal for this course and define what we are striving for. Here we have a general view of the Geosteering desktop, the main tool for every engineer working in shifts and making trajectory changes while drilling. And our ultimate goal is to understand the routine process of everyday geosteering work and figure out in detail what's going on in this picture. At first, it might seem like there are many complex elements, but no worries, step by step everything will become clear. So let's break down the Geosteering desktop on its main components. On the left side, we have the structure map, which shows the behavior of a specific target layer. In upcoming video number 3, we will learn how to read it and understand what the different colors mean. On the right side, we see an offset well, which serves as the foundation for building the geosteering model. We will explore what kind of wells can be used as offset and what requirements they should meet. In the upper part of the picture, you can see tracks with real-time curves. There is a whole part 2 of our course dedicated to BHE components and LWD tools. It includes 7 lessons where we go over the main LWD methods, like gamma ray resistivity and neutron density logging. We will also learn how to tell sandstone from shale, coal from hard layers, and what image log is. And finally, the most interesting part, the geological cross-section, or the geosteering model itself, which shows us the position of the wellbore relatively to the formation. In part number 3 of the course, we will discuss in detail how to adjust it by using model and stratigraphic methods and other modern geosteering tools. So, we've broken down one big goal into smaller steps, and today we start from the very beginning, with the definition of a well trajectory and its key components from a geosteering perspective. Let's get started. So, what is trajectory? It is the path along which the drill bit moves while drilling, a three-dimensional line in space. To describe this line, we need 3 coordinates. We use measured depth, inclination, and azimuth, which are analogous to spherical coordinates, 1 linear and 2 angular. Measured depth is the total length of all elements in the drill string below the rotary table. There is a whole knowledge-intensive discipline focused on these measurements, which is called the Survey Quality Control Service. We briefly touch on it at the last part of the course, but looking ahead, we can say that MD, inclination, and azimuth are the only parameters in the survey report directly measured, while the other values are calculated. It means that if there is an error in measured values during drilling, it might significantly affect the calculated ones, and some of them, like TVD, are critical for geosteering. Also, all LWD logs are based on MD, that's why the importance of this measurement can be overstated. MD is measured on the surface using hook load and drawwork sensors on the rig, while inclination and azimuth come from the MLWD tool downhole. The quality of these surveys is the responsibility of MLWD engineer. Okay, let's break down inclination and azimuth using a simple example. Imagine we have a horizontal well and a random point A on its trajectory. There are 2 planes, the horizontal plane or plan view and vertical plane, which we also call cross-section or curtain section. Inclination is the angle in cross-section between the vertical line and the trajectory. For vertical wells, inclination is less than 5 degrees. Deviated wells might have inclination up to 60 degrees, and if the well has inclination greater than approximately 85 degrees, we consider it horizontal. Typically, inclination values don't exceed 93-95 degrees, but it really depends on the specific project. When we deviate from vertical, we do it along certain cardinal directions. That's why inclination is inextricably linked with azimuth, the angle in the horizontal plane between north and the trajectory. North corresponds to 0 azimuth, east to 90, south to 180, and west to 270 degrees. In our example, we observe that the well has azimuth 45 degrees at the beginning, and after point A, it turns gradually to 90 degrees. So, we've described measured values, now let's consider some essential calculated values. First up, TVDSS. It is the distance from point A to mean sea level. Why MSL? Because it's a consistent and reliable reference and all geological markers and horizons are tied to it. Next, DLS or dogleg severity. It is the intensity of the borehole's curvature. Think of it as the rate at which inclination and azimuth change. A high DLS means sharp curvature and rapid trajectory changes, but it can lead to high friction and potential issues while drilling or well construction. Of course, if we are drilling in the productive layer and leave it at some point, geologists always want to get back into reservoir as quickly as possible using a high DLS. But what's the point if, for example, you will not be able to run a fracture assembly afterwards, right? That's why in certain projects there is a specific DLS limit, and geosteering engineer has to keep it in mind when suggesting trajectory changes. And finally, we have one more measured value which describes trajectory in the space. It is the drill floor elevation, the distance from the drill floor to MSL. It is measured when the rig is positioned at the well site. Usually this value stays constant throughout the drilling process, but sometimes it might be changed due to several reasons while construction. And since this value significantly affects the geosteering model, you need to be sure you have it up to date. Okay, now let's take a look at a real example of a well trajectory in a cross-section. The black line shows the actual well up to 3000 meters MD, and after that we have the red planned trajectory. The vertical section lasts up to approximately 400 meters MD, and here is the first 4 surveys from the very beginning. As we can see, at 64 meters MD, we start deviating from the vertical. Azimuth at first is 0 degrees, then jumps to 29 and 48 degrees. Why does it change so sharply? The root cause is the physics of azimuth measurements. The point is, it's very challenging to MLWD sensors to get accurate azimuth readings in vertical sections, and we cannot fully trust azimuth data when inclination is less than around 3 degrees. That's why azimuth in the vertical section is often interpolated or even spiralized, meaning values 0, 90, 180 and 270 degrees are assigned in sequence until azimuth measurements become stable. Okay, next is the vertical depths. As you can see, TVD starts from 0, while TVDSS starts from drill floor elevation value. And as the rule, TVD is positive, while TVDSS comes with minus sign. When inclination is less than 90 degrees, the vertical depth increases in absolute value, and vice versa. And the last column is DLS. In the second survey it is 0 because we didn't change neither inclination nor azimuth in the first 30 meters MD. Then inclination and azimuth start to change a bit, so DLS is no longer 0, but it remains low since we usually try to stay close to vertical in the upper section. Okay, now let's take a look at the build-up section after 2500 meters MD. Here we are increasing inclination and turning azimuth at the same time, which results in DLS of more than 2 degrees per 10 meters. As you can see, TVDSS is still increasing, but more slowly than in the vertical section, because of the higher inclination. And finally, we have the horizontal section, which is presented as the planned trajectory. That's why we see rounded depth values every 30 meters. We observe a stabilization in inclination and azimuth values and also 0 DLS. This is a common approach to plan the final section of the well, where the completion equipment will later be run in. We can also observe that inclination greater than 90 degrees leads to a decrease in the absolute value of TVDSS, because we change vertical direction and start heading back toward mean sea level. Alright, we have covered the most important components of the well trajectory for a geosteering engineer. Hope you like this video. Remember, you also have the opportunity to enhance your practical skills. Together we will work in StarSteer to apply all modern geosteering tools and drilling simulators, so you can feel like a true geosteering engineer in real time. So stay tuned and give this video a thumbs up. In the next lesson we will explore the target layer and formation deep. See you then. Bye bye.